We've been spending a lot of time talking about linear transformations, but in particular, we've been speaking a lot about matrix transformations, and it turns out there's a reason for that. So let's let T be any linear transformation from Rn to Rn. Then it turns out that T actually is a matrix transformation. And this would be the matrix. Okay? We say, in this case, matrix A is the matrix that induces the linear transformation T. Okay? Let's prove this. So what I'm going to do is I'm going to take any vector in my domain. So let x be the vector x1, x2, all the way to xn in my domain Rn. Okay? Rn is the domain of the transformation. Observe that vector x is equal to x1 times vector e1 plus x2 times vector e2, and so on, all the way to xn times vector en. Okay, where e1 to en is the standard basis of Rn. Okay, this shouldn't be a surprise. We are aware of this. Just a concrete example, just in case you can't remember what the e's are. In 2 dimensions and 3 dimensions, we usually use vectors I, j, k. But in 4 and higher dimensions, we will use vectors e1, e2, and so on to give us standard basis vectors. So for example, if I have the vector 1, 2, 3, 4, that's 1 times the vector 1, 0, 0, 0 plus 2 times vector 0, 1, 0, 0 plus 3 times vector 0, 0, 1, 0 plus 4 times vector 0, 0, 0, 1. Right? And these vectors are the standard basis of, in this case, R4. So it'd be E1, E2, E3, E4. Okay? I could apply the same strategy to any vector in any number of dimensions. So that's all I'm doing here. I'm just expressing my vector as a linear combination of the standard basis. The coefficients of the standard basis are just the components of the vector. All right? But we want to apply a linear transformation. So then the transformation on vector x is just the transformation on the linear combination of the standard basis that gives us x. And because it's a linear transformation, linear combinations are preserved. So this is going to be equal to x1 times the transformation on the first vector in the standard basis plus x2 times the transformation on the second vector in the standard basis, and so on. Okay? Now, as we remember, if we have a linear combination of vectors like we have here, right? This is a linear combination of vectors. Scalar times a vector plus a scalar times a vector plus a scalar times a vector. Okay? If we have a linear combination like we have here, we can represent it as a matrix vector product. Specifically, the matrix, the columns of the matrix are the vectors in the linear combination. So TE1, TE2, all the way to TEN. And the vector has components x1, x2 to xn. But this matrix here was just the matrix that we mentioned here. Just matrix A, mentioned in the theorem, right? And the vector with components x1, x2 all the way to xn, that's just the vector x that we started with. And so we can write this as matrix A times vector x. And that is the transformation on x is just a matrix times a vector. And that's the definition of a matrix transformation. Thus, T is a matrix transformation. With, because the matrix here, matrix A, the columns of matrix A are just the transformation on the standard, the vectors in the standard basis. We call it the standard matrix of the transformation. Okay, so transformation T is induced by matrix A, but matrix A is the standard matrix of transformation T. Okay, so know what this means. Okay, every single transformation from Rn to Rm is going to be a matrix transformation. And we can figure out what the transformation is just by seeing how the transformation affects the vectors in the standard basis. Okay? And we also know every matrix transformation is a linear transformation. So a linear transformation from Rn to Rm is linear if and only if it is a matrix transformation. All right? Now, be aware that this doesn't mean every possible linear transformation is a matrix transformation. Only linear transformations that have a domain in Rn and a codomain in Rm. So for example, if I have some other transformation from some other vector space, which may be just a subspace of Rn, to some vector space W, that need not be a a matrix transformation. It could be a linear transformation, but it need not be a matrix transformation. The domain and codomain here matter. Okay?